We are diving into the paper DR Tulu, Reinforcement Learning with Evolving Rubrics for Deep Research. This one is a really big deal for creating research agents that are both high performance and actually affordable.
It really is. The problem they're tackling is, well, it's a huge one. Existing deep research or DR models, particularly the open source ones, they just really struggle with long-form, open-ended tasks.
And why is that?
They're typically trained with, static reward systems.
Yeah.
Things like verifiable rewards, which are fine for simple questions, but they just don't capture the complexity of real research.
So the key innovation here is something they call reinforcement learning with evolving rubrics, or RLER.
Exactly.
So instead of a fixed scorecard, RLER trains the agent using these dynamic rubrics that actually co-evolve during the training itself. They're constantly adapting and grounding themselves in real-time search knowledge.
Which provides this incredibly relevant discriminative feedback, and the results are, well, transformative. DR Tulu-8B is the first open model that's been built specifically for this kind of long-form deep research.
And it really shows.
Oh, yeah. It substantially outperforms every existing open competitor, even models that are much, much larger, like the Tumyi Deep Research 30B model. It beats them across 4 major benchmarks.
And it's not just outperforming open models. It actually competes with proprietary systems like Gemini 3 Pro plus Search on Performance. But for any engineers listening, the cost difference is, frankly, disruptive.
It's astounding.
DR Tulu-8B sits on the Pareto frontier for performance versus cost. We're talking something like $0.019 per query.
Which is almost 3 orders of magnitude cheaper than something like OpenAI Deep Research, which can be, $1.80 per query?
It's incredible. It's really proof that a sophisticated methodology can absolutely outperform just throwing more parameters at a problem.
For sure.
Okay, so let's unpack that initial challenge. Before RLER, what was it that made these deep research models, the ones doing multi-step planning, searching, synthesizing, so hard to train and evaluate? What is this evaluation gap?
Well, you have to think of a DR model as like an autonomous researcher. It has to strategize, use tools, pull in facts from all over, and then synthesize it all into a coherent, long-form report with citations.
Right.
The traditional method for this, RLER reinforcement learning with verifiable rewards, is great for short Q&A. You can check if a single fact is correct.
But if the output is a 2,000-word research paper, the idea of correct just explodes in complexity.
Exactly. That's the evaluation gap. For a long-form response, the desiderata, what makes a response good, is often really underspecified. You can't just check for fact X.
You have to check the synthesis, the relevance, the citation quality.
The depth, all of it. And you have to check it against this vast dynamic body of world knowledge. A static rubric is just going to miss 90% of the nuance you need for high-quality research.
So the core idea is that if the goal itself is dynamic and knowledge-intensive, your reward function has to be dynamic and knowledge-intensive too.
That's the heart of it.
And that's where RLER comes in. So tell us about the philosophy behind reinforcement learning with evolving rubrics.
The philosophy is actually elegantly simple. It's stop relying on generalized, fixed criteria.
Okay.
RLER insists that the rubrics must be grounded in external search knowledge, be specific to the instance you're querying, and this is the critical part, they have to co-evolve with the model's own behavior.
And that last part gives you what they call on-policy feedback.
Precisely. It tells the agent how well its current behavior is working right now for that specific task.
Let's get into the mechanics of this then. They split the rubrics into 2 different components. Let's start with the foundation, the persistent rubrics, which they denote as...
Right, these are the stable core. They're generated before the RL training even begins, based only on search results from the initial query.
And grounding them in external search is really important. Why?
Because it ensures they are highly factual and assertive. The paper points this out with a great metric. These search-based rubrics have over 50% assertive claims.
Compared to what?
Compared to only 22% for closed-book rubrics that are just generated by an LLM making stuff up. So these persistent rubrics establish that factual baseline the agent absolutely has to meet.
Okay, so that's the foundation. Now for the really innovative part. The evolving rubrics, or the RLERs. This is the active learning component that makes RLER so dynamic. How are these generated during a training run?
This is where the system gets really smart. For every single question, RLER compares successful rollouts of the policy. So what the model did well with unsuccessful or flawed rollouts.
A contrastive approach.
Exactly. And by contrasting these, the system generates brand new rubrics. So you get positive rubrics, which identify new relevant knowledge or maybe an effective synthesis pattern the agent just stumbled upon.
And, maybe even more importantly, you get negative rubrics, which I assume are there to fight reward hacking.
That is their entire purpose. The negative rubrics are designed to summarize common, undesirable behaviors that pop up as the model learns to game the system.
Do they give an example?
A great one. The base Quen model, during early training, started spontaneously generating chunks of unwanted Python code in its answers.
Right, a classic attempt to satisfy some low-level token reward without actually improving the research quality. That is a textbook failure of a static reward system.
Absolutely. A fixed rubric would never have anticipated that generating code would be a problem.
But RLER did.
Right. Its contrastive mechanism spotted this weird behavior and immediately generated a negative rubric that penalized inserting non-answer content like Python code. This essentially gives the reward function an immune system. It learns to suppress these emergent flaws in the policy.
Which creates a much cleaner learning signal over time.
Exactly.
So you have this dual feedback loop, a positive one for good research habits and a negative one to stamp out emergent hacking. But if you're constantly generating new rules, how do you stop the system from getting completely overwhelmed? That rubric buffer must get huge.
That's a great question. They have to keep the reward signal highly informative and compact, so they have a buffer management strategy.
How does it work?
Every rubric is scored against the rollouts. If a rubric has zero variance, meaning it's either always satisfied or never satisfied, it gets removed immediately.
So it's not helping distinguish good from bad. You're just pruning the dead wood.
Precisely. And then they only keep the top Quimax rubrics, specifically the one showing the highest standard deviation in reward.
So you're only keeping the rubrics that are the most discriminative, the ones pushing the model at its current performance boundary.
Yes. That focus on variance is absolutely critical for efficiency.
Okay, before we get to how they actually built the model, let's touch on the auxiliary rewards. These are more like structural supports, right?
It's a perfect way to put it. Alongside the main RLER score, they include these small, targeted auxiliary rewards, format rewards for structure, search rewards for using tools well, and citation rewards for attribution.
They're just the low-cost signals to encourage good hygiene. So RLER is the brain that figures out what good research looks like. Now let's talk about the body. How did they actually build the DR Tulu-8B agent? The pipeline started with supervised fine-tuning, or SFT.
Right, and SFT provides that critical cold start. The base model, Quen 3.8b, it's powerful, but it doesn't intrinsically know how to plan or use tools or format citations.
So SFT is like a foundational boot camp for becoming an agent.
It is. They curated about 16,000 data points for this, mixing long-form research tasks from data sets like OpenScholar and Search Arena with short-form verifiable Q&A like Hotpot QA.
That blend is important, I imagine.
Very. It ensures the model learns the agent workflow while still keeping its general purpose capabilities. And they made sure the data was high quality by using a very strong teacher model, GPT-5, actually to generate the initial trajectories, which were then filtered really rigorously.
And once the model had that basic grasp, they moved into the online RL phase.
Yes, focusing exclusively on 9,000 long-form research questions, and this time using RLER.
They used a custom variant of GRPO for the training, which is a stable and efficient RL algorithm. But from an engineering perspective, the detail that makes this whole pipeline work feels like the asynchronous tool calling.
It is absolutely the game changer for training efficiency. Think about it. In an agent pipeline, a huge amount of your wall clock time is just spent waiting for external API calls.
Waiting for Google search or some paper database to return results.
Exactly. If you have to wait for those latency spikes every single time, training becomes excruciatingly slow and expensive.
So how did the asynchronous mechanism solve that bottleneck?
Simple, but brilliant. When the agent needs to make a tool call, the rollout for that specific task is just paused. But, and this is the key, the inference engine doesn't wait.
It context switches.
It immediately context switches to work on other generations, other rollouts that are ready to go. This massive overlap of generation time with the external API latency just dramatically slashes the overall wall clock time.
And it lets them achieve much higher concurrency, even with strict API rate limits.
It's a superb piece of infrastructure work. And it's all built into their custom fully released agent library, Drage Agent Lib.
The engine room that supports all this.
For sure. And that library is worth looking at if you're building agents. It's got a unified tool backend, supports things like Google Search and web browse, and manages high concurrency, caching, and uses process locks to handle those critical API rate limits without getting banned.
That entire stack is what allows an 8 billion parameter model to punch so far above its weight. So let's look at the numbers and quantify that performance and that cost efficiency.
Okay, so if we average the performance across the 4 big long-form benchmarks, SQAS 2, HealthBench, Research QA, and DR Tulu-8B with RLER gets a score of 63.7%.
And the closest open competitor.
That would be Tangi Deep Research. It's almost 4 times larger at 30 billion parameters, and it hits 50%. That's a nearly 14-point gap. It's enormous in this field.
And the RLER phase itself is where most of that gain comes from, right? Added between, 4.5 to 14.5 percentage points over just the SFT baseline?
It did. But what's really compelling is how it stands up against the proprietary closed systems. DR Tulu-8B is right there in the top tier. It averages 63.7%, while Gemini 3 Pro with search is at 57.0%, and OpenAI Deep Research is at 64.9%.
So an 8B open model is matching or even slightly exceeding some of the biggest proprietary systems.
It is.
But the real victory here is the cost. When you talk about the Pareto frontier, you have to visualize that graph.
Right. Imagine a scatter plot. Vertical axis is quality. Horizontal is cost. Most models are kind of clustered in the middle, or they drift way out to the right, the expensive side.
And DR Tulu-8B.
It's sitting way up in the top left corner, high quality, ridiculously low cost.
And those cost numbers really are the headline for anyone managing a budget, $0.019 per query. What does that mean for a small research lab or a startup?
It means access. It means you can actually do this stuff. Look, running 1,000 deep research queries with OpenAI's system would cost you $1,800.
And with DR Tulu?
$1.90. This just fundamentally changes the economic viability of building agentic systems. The next most cost-effective open model is 10 times more expensive.
This opens the door for so many more people.
Individual researchers, educational institutions, they can all use high-quality, deep research agents now without needing massive computational resources.
And a big part of that cost efficiency is its learned ability to use tools adaptively. It doesn't just default to the most expensive tool, does it?
It does not, and that is key. On scientific tasks like the SQA V2 benchmark, it relies almost 97% of the time on the paper search tool.
Which uses the free Semantic Scholar API.
Right. Free search means huge savings on marginal cost.
But it's not rigid. It knows that academic papers aren't the only source of truth in the world.
Correct. When the task shifts to something like general knowledge or medical queries on HealthBench, its reliance correctly shifts to Google Search and web browse. They even analyze the domains it searches.
Oh, that's interesting.
For HealthBench, the model prioritizes high-trust sources like cdc.gov and mayoclinic.org. This adaptive tool selection is a direct result of RLER, and it leads to both higher quality answers and lower operational cost.
Okay, let's shift focus to the qualitative improvements. We talk about scores, but what does RLER actually do for the quality and the trustworthiness of the final report?
The impact on attribution quality is probably the most impressive result here. If you look at the fine-grained metrics on Score AV2, the RL phase saw citation precision jump by 23.3 points.
Wow.
And citation recall jump by 22.1 points over the SFT baseline. This is huge. For a technical audience, this is the difference between an answer that might be misleading and one that is reliable and verifiable.
For anyone using these models for, say, professional reports, this isn't just a score jump. It's about reducing the human fact-checking time. It builds immediate confidence.
And beyond just citations, the subjective quality metrics also went up. Comprehensiveness increased by over 5 points and depth by over 6 points. RLER is genuinely training the model to write a better, deeper research report.
They also showed that it generalizes really well. They tested it on an out-of-domain task, genetic disease QA.
Right, a clinical data set that requires this complex synthesis of evidence for therapeutic eligibility. This is a scenario where you need deep domain expertise and scrutiny is incredibly high.
What how to do?
DR Tulu-8B outperformed the SFT baseline and even beat specialized clinical agents like AI2 Scholar QA. It really demonstrates the transferability of its research skills.
What was the key insight from that specific clinical domain?
Its strength really shown in evidence support and evidence synthesis. In expert domains, users demand to know why a model made a conclusion.
You need to see the receipts.
You do. And DR Tulu provides snippet-level citations. That means the citation points directly to the sentence or paragraph in the source that supports the claim. Most open models just cite the whole article.
That snippet-level detail makes human verification so much easier. It's vital for building confidence in expert applications.
It is.
So this deep dive into DR Tulu really shows an accomplishment across both methodology and engineering. They've created a fully open, small 8B model that achieves state-of-the-art open performance on these really hard, long-form tasks, all while being incredibly cost-efficient.
And the RLER methodology, moving beyond static evaluation to these dynamic, search-grounded, evolving rubrics, is undeniably the engine driving that success.
It feels like a definitive shift in how we should approach reward design for complex agents.
I agree. But even with RLER, the research team highlighted a really important ongoing challenge in RL.
The famous train-test mismatch problem.
Exactly. They noted that the models that got the absolute highest training reward didn't always perfectly correlate with the best scores on the downstream evaluation benchmarks.
Why is that?
Because the training time judge, in this case it was GPT 4.1 mini, is operating with one set of evolving rubrics. But the final evaluation uses different criteria, often expert annotated or benchmark specific ones.
So this raises a really important question for all of the researchers listening to this. How can we design reward functions, even incredibly sophisticated ones like RLER, that are truly agnostic to the specific judge model used during training?
How do we ensure that the skills the agent acquires robustly generalize across all the diverse expert annotated evaluation setups you find in the real world? That, I think, is the next great frontier for agentic research.